Hello, this is my NEA prototype. Today I will mainly be showing the interactive mode aspect of my program. This involves all the mathematical and physical operations used for my projectile motion simulator. But before we do that, let's have a look at the main menu. So this is the first thing the user will be presented once the initial program has been set up. Right here. As you can see, the GUI I've used for my software was PyQt5, where the application Qt Designer right here, if I just load up, just give it a few moments. Right here. Assisted me to create a layout of all my text edit options and buttons, nothing more. Near the bottom of this .py file, there is a function here that is activated when this button, Open Interactive Mode button, is clicked. Right? And this will generate a new window catered things all interactive mode wise. Everything for this window is controlled in this interactive mode window.py file, and unlike the main menu, the UI wasn't entirely made by Qt Designer. Instead, I also imported figure canvas from the module matplotlib, which is used to display my graph. I've also imported the module numpy, mainly because it's easy to convert between degrees and radians, as well as for other functions in my graph, which you'll see later. So this is most of the code for my GUI. And over here is where I connected specific buttons that have been pressed to their corresponding functions. Here is the main menu button that closes this window. Right here. I won't press it yet. As well as a reset simulation button and a start simulation button. So reset and start. No, reset variable, sorry. Below this is my placeholder layout for the distance and velocity time graphs. Basically, this is just a widget container that adds these graphs to be visible on this window. The layout of the graph, size, and location is also set here. So rather than them being opened in a new window like they normally do when you open use matplotlib, they could be just displayed on this window, which is quite convenient for the user. Just note down here that this reset variables function is called during the creation of this window already. And this is to set the initial and suggested values. For example, the vertical acceleration is set to 9.81, which is the same as the gravitational accelerations all objects experience on Earth, which makes it a fundamental constant. But there's always an option to change these values should you wish. So you also have the acceleration for horizontal components, which is normally 0, unless if you have drag involved. Now, with the start simulation function, this is where most of the mathematical and physical operations are set and executed and called throughout. You may notice that time has been split into horizontal. Oh, wait, sorry. You may also notice that our values have been split into horizontal and vertical components. You'll see this minus time. You'll see in a minute, but we set the time variable into both horizontal and vertical components. You'll see in a minute how this will be used. First, there are calculations done involving the initial horizontal velocity and vertical velocity, and these include launch angle, if inputted by the user, as well as wind and drag adjustments. A bit of debugging here to make sure that the initial horizontal and vertical velocities become 0 from these calculations, not when they have been inputted. This is so that they can be set to none, which is needed so that we dismiss them when counting each value for each component. You'll also see that later. And over here is where you can see some of the calculations that I've done here for my initial a horizontal and vertical velocity. As you can see in this function, launch angles calculations, NumPy is being used to convert the user's input of launch angle into radians, as it is a natural unit compared to degrees. Bear in mind the user also has the option to input their angle in radians as well. Right? Same thing with get wind values. Regarding the wind direction, you can also change that. That's also converted to radians. And here are the functions for applying the wind adjustments, which is just adding on to the horizontal vertical velocities depending on their direction. And then after this is one of the most critical points of my actual code. You go to this function being called count values. Now this function here is critical because we must count each value for each component. Here you can see the convenience of splitting time into horizontal and vertical components uh, uh, because it is more efficient to read each variable type for each component and store them in their own dictionaries accordingly. Each value is also converted to SI units to make future calculations easier uh, to manage and solve. As you can see here, the function is called and it is all converted. Distances, speed, and time over here. And this is based on if the Boolean value of convert to SI unit is true or false, right? And if each component has a certain threshold of values, uh, so here, then uh, then two VAT calculations can be executed to solve the missing values for each component. So right here are the equations of motion, and these are the this is basically what I'll be using for my CVAT calculator. I also have speed, distance, time equation involved here as well, just if you're wondering. So for my calculate suvat function, once this is called, a lot of logical operations are done here, deciding on which variable types have values and which don't for each component. This is called twice to separate the horizontal and vertical components. Uh, and at the end of this function, you have, you could see if, what was it? We then see if the graph can be made based on if we have enough units for velocity, distance, time, and acceleration for both components. If this is true, then the code will be executed in the plot canvas class here, right here. Here you can see the graph's initial setup using NumPy again to store an array of zeros, which is displayed by the lines here. It's also used to separate the time intervals in accordingly. And the final three functions here, so update graphs, generate graph data, and update with inputs, essentially just update the graph based on our values by taking several small slices of time, then using our spin box to determine this number right here. So when we have this spin box, it will determine the number of readings taken for the graphs, and then calculating the velocity and distance at different at these intervals. These values will be stored in multiple arrays, each array storing a particular component for both graphs. Then they are placed into their respective axes and then drawn. So I have some practice values here, over here, and now I'm going to test it with this main window. So I have my initial vertical velocity to be 10, my initial horizontal velocity to be 15. This is test case 1, and my time is equal to 2.5 seconds. Then once we start the simulation, we get these values here. You can see that my values seem to be correct. I could also add the launch angle to change some differences, but first I want to show you how the graphs work. Seems pretty accurate because the horizontal velocity would remain constant if there's no acceleration, so that checks out. And with the launch angle, uh, you can see the change in values that occur as well. And then if you can also increase or decrease the drag coefficient as well if you wish. Sometimes it doesn't make a huge difference. And you can also change the wind speed, which can also increase their velocity depending on the direction it's in. So that's it for my code, and bye.